Hello everyone and welcome back to my channel. So in the previous video I had explained about how we can optimize recursive Fibonacci series with the help of memoization technique, and I'll also promised you that I'll be helping you in writing the optimized code. So if you haven't watched my previous video, I would highly recommend you to go first and watch that video before you come over to this one. So I'm going to start writing the Java code in the usual environment that I prefer, that's BlueJ. I'll create a class, call it OptiFibo. Since the class is created, I'll just eliminate all the contents and I'll define the usual inputs that we do in our Java code. This is the one that's for input and output, and the other one that's for scanner and printing the array classes. That's util. That contains all the utilities that we need. And then I define the class that I'm using, that's OptiFibo, and I start writing my functions inside that class. The first is the main function, which is called, before anything else in the program, the main function. So I'll define my scanner class SC to take the input from the user of the number of Fibonacci terms that he requires or he wants to be printed. So int n is the variable where I'm going to store the input. sc.nextInt. Wait, but how will the user know that he has to input a value? Yes, we need to print an output to the console indicating the user that now he needs to enter a value. So I'll be more polite, saying that please enter the number of Fibo terms you want. Right? So that's how I've defined things here. The input is done. So now I need to create the lookup table for memoization technique in order to optimize the code. So you have int, since all of the terms of Fibonacci are an integer to be particular, we have new int of what should be the value. The value should be till n, so it goes from 0 to n minus 1. That's how indexing is done in case of arrays, as you know. So I'll just initialize the initial values of the lookup table. Those are the initial values of the Fibonacci series as well. That's for 0 it's 0, and for 1 it's 1. And then I'll go to the for loop. Since we have already defined the first two terms, I'm gonna go and define the other terms. So that's less than lookup dot length, and what's the error? Oh, I forgot a semicolon here. My bad. What did I do? Okay. So I just go down and take the input. But why am I losing this for loop either? It's just because I want to store -1 and all the rest values. So initially all the other values except 0 and 1 are initialized or instantiated with -1. Not instantiated, actually initialized. Instantiation is something that we use for objects in particular. And then I'll call a function, my lovable Fibo function. So it will start with what will it have? I'll send the lookup. I can also define it as a global variable, the array as a global variable. I don't want to do that, so I'm passing it as a argument to the function, and then I'll pass the argument of n as the function. Oh, it's giving me an error because I have not yet created the function. So I'm going to create the function as static, so we don't require objects to be created in order to access that particular function. The return value is going to be int, which you will eventually figure out why I'm doing it. It will be unveiled in the further part. That's int of Fibo, and what that will be, it will be just reduced to int of Fibo. What we have, we can just define it as lookup here as well. You can emulate the names if you want, or you can keep another name as you wish, but I prefer to keep it the same. So it's int n and in lookup. So what's the first check? The first check is if the lookup of n, hey, is at -1. Then going to this part, or else just return a of n. As I've explained in the previous video, the value is already there, you just return the value from that array. So inside we have to do another two checks. Well, if n equals 0, so is it equal to 0? If it is, then return a of 0, or you can also return 0 if you want. So since we have already defined, what's the use of defining that? So I just return it. And then if n is equal to 1, what we do, we return a of 1. And finally, oops, I forgot if here. It's another condition, right? So finally, for else, I'll just store the values in a of n. So if you have seen my previous videos, I used recursive in this case as well. So that proves that I'm not using memoization technique, but here I am. So if a of n will be equal to, I'll be recursively calling that function with the lookup I have, the recent lookup. So since it's an array, if you have studied call by reference, it does not matter if you send it as an argument. If you define it globally, any changes in the array will always be reflected in the emulated arrays as well, since it uses the concept of pointers. So for Fibo, we have lookup as well as n-1. That's the first part, and I'll copy the second part. Let's copy and paste it here. So that's n-2. And I'm done with the thing that I have to do. I don't know why I always prefer a here. It should be lookup. It's the usual intuition that I do. I'm extremely sorry for that. So am I done? It's lookup of again here. So it shall compile successfully, and I'm gonna print that system.out.println. So you can also print it separately by iterating through the array. I always prefer this one because it saves me a lot of time. What is it? It is nothing but the lookup that we want. So does the thing for me. I'll just go inside in it, and it's working. So to ask me, I'll just clear the screen, stop the execution again. And since it has started executing, I'll just put 5, and what's the error that it gave me? So if lookup of n. So the reason why I'm getting this error is pretty obvious. It's just because I'm sending the value of n, and since I've already explained, if I take n is equal to, it's nearer, if I take n is equal to 5, then it gives me what set of terms? It gives me 0, it gives me 1, it gives me 1 back again, and then 2, 3, 4, 5. Sorry, 3, 5, and if it's still 5th term. But what I just want are the 5 terms, and that is how I've initialized the array, and that is why it gives me array index out of bounds exception. So I'll just put it n-1, and now it should work all fine. So I'll just execute it now, and then I shouldn't get the error right now. So it prints the first 5 values. How does it actually optimize the value? So in case of optimization, let's say you have you need to calculate till f of 4. So I'll take f of 4 for n is equal to 5. As I said, n is equal till n-1. It splits up into 2 since if you haven't watched my previous videos, please do check them out in order to understand the process. It's f of 3, and then it gets split into f of 2 and f of 1. And then finally what I have is f of 1 and f of 0. So the first function call, let's get it off the stack. Let's consider here I'm just putting the stack values. The very first function that is executed is f of 1. Very first function that's executed is f of 4. So it's not FIFO, it's LIFO, that's last in first out. And then we have f of 3, which depends on values of f of 2. And then we have f of 2, and finally we have the function called for f of 1. So for f of 1, it returns, since it's already there in the lookup table, we have, let me write down the lookup table here. It's 0, 1, and then minus 1, minus 1, minus 1 for those 5 terms. And for 1, it looks into the position of 1, since it returns a of n in the code that we had written. It returns lookup of n, right? So yeah, lookup of n. So it will return 1, so we'll get the value of 1. This will be eliminated. Now we'll have f of 0 now. So here f of 1 is 1, and then for f of 0 it will get the right call, and for f of 0 we'll have 0. So for f of 2 gets executed, so this gets cancelled, and we have f of 2 equals 1. So again for f of 1 there will be another function call. So the total number of function calls currently is 1, 2, 3, 4, 5. There are 5 function calls, and then we have another function call for f of 1. F of 0 gets cancelled, and we have a function call for f of 1. We already know what f of 2 is through recursion. And then f of 1 is, again it will look back into the lookup table, and here what it actually does is, since once f of 2 becomes equal to 1, it will eliminate this and it will put 1 here. And then for f of 1 it's 1 back again, so it's 2, so it will put 2 here. And the most fascinating part is, here in case of f of 2, normally how it does is, it calculates, it again gives 2 more function calls. That's for f of 1 and f of 0, which will be eliminated in this case. There will be no further function calls. So these 2 function calls will be eliminated, and will directly have f of 2 will be looked into the lookup table. So for f of 2 it will be lookup of 2. For f of 2, this is f of 3, I'm sorry. It will look here, that's 0, 1, 2. Take 1 here, and finally we'll have f of 4, which is equal to 3. So that is what is printed. So 0, 1, 1, comma 2, 3. So currently you might be thinking how many function calls there have been called. So let's get in hierarchically. We have f of 4, then we had f of 3, we had f of 2, then f of 1, we also had f of 0, and after both of these, after all of them are done, we had f of 1 back again. Another function call, right? So we had f of 1 back again, that's it. So then finally f of 2 is not called twice here. So it only gets us 6 function calls, which actually reduces it with how many set of function calls? With 2 set of function calls, or usually it should have been f of 2, and then for f of 2 we had f of 1, f of 0. So it reduces 2 function calls. So that's how it optimizes our program. The lookup table optimizes our program. So coming over to the time complexity, space complexity is perfectly O of n, and since it depends upon n right now, that's the lookup table, the number of function calls are reducing, right? So the time complexity will also become equal to O of n. So since for a value of 4, for n equals 4, n equals 4, the number of function calls required are 6. But for 1.6 raised to 4, it would have been more. Like it requires 8 function calls. So let me estimate the value of 1.6 raised to 4. What will that be? 1.6 raised to 4. So it gives me round about greater than 6 function calls. Actually it should be nearly 8 function calls, so which is greater than this value. gives me 8 function calls. So here it reduces to 6. So you can say that to some extent it depends upon O of n. So this is the optimization problem for memoization technique. Thank you for watching. Please like, share and subscribe for more interesting content. Thank you and have a nice day.